Hello, and welcome to today's statistics lesson. We're going to talk about similarities and differences of a sample and a population. In our current topics, we start talking about measuring means of samples and comparing them to means of populations and how we can use information gained from a sample to understand something about an entire population, even though the entire population was not measured. So we have two things, a sample and a population. And basically a sample is a subset of the population. If you take data from a sample, you're asking some of the population. If you take data of a population, you're trying to ask all of the population. Now, an example of asking all of the population would be the census. An example of asking some of the population, or subset, would be if you wanted to know something about the students at our school. You might just go to different classes and ask or put out an online survey, and not everybody would respond. Not everybody is included in the sample, but everybody is included in the population. So we can sometimes use results from a sample if the sample is well taken to make conclusions about a population. So to use the results from the sample, though, the sample must be chosen in an unbiased manner. We talked about this at the beginning of the course, too. And we also talked about this next row. If you get data and you took it from a subset of the population, it's called a statistic. If you asked all of the population like they do in the census, it's called a parameter. That's a technicality. It shouldn't haunt you too much if you don't get that, but the sample goes with the word begins with S, the population goes with the word begins with P. That makes that a little easier. Now, symbols are always an issue when we start talking about math and the language of mathematics. The mean is what you would call the average. You add up everything. If you wanted the mean of 5 numbers, you'd add up the 5 numbers, divide by 5. If that mean is of a sample, of a subset of the population, we use this X bar. If the mean is from the whole population, we call that mu. That is called mu when it's for the whole population. So those two both encompass the same idea of an average, but this is just from some things you surveyed or had numbers on, and this would be from the whole population. Standard deviation, if it's from a sample, it's with the S. If it's from the population, it's this symbol here that looks like a kind of an O with a curl on top, and that is called it's a small sigma. Okay? Now, standard deviation we just did, proportion or probability or percent of the population. That's what we use P. When we did probability distribution tables, the probability of getting 2 heads when you flipped a coin was P of 2. For a sample, we use P with a little hat on it, and we literally read that as P hat. That looks so fancy, everybody gets thrown off. That is just the probability. If you're just working with a subset of your population, instead of saying P, we say P hat. Hopefully that won't tangle you up too much, but you're going to see that in the reading. You're going to see that in the notes. You're going to see that in other videos. I want to make sure you understand that. It just means the probability, the part of the population, usually expressed as a decimal. Rather than the part of the population, it's the part of the sample that exhibits some characteristic. Now, for the statements below, hopefully this will let me do this. Shut this off. For the statements below, it does not let me scroll. There we go, sorry. Apply to data collected from a population by taking multiple random samples. So sometimes when we can't ask everybody, we can take a bunch of different samples, all of the same size, pick some size n, it could be 100, n can be 50, from the population. So if we wanted to find out something about students at our college, we might ask, several of you might go out and you'd each ask 50 different people. You'd each ask 50 people, and then we would take the mean of each of those groups of 50 and then take the mean of that to get the mean of the population. It turns out that works out pretty well if you take enough data. Now, for all populations, regardless of their shape, so let's say whatever we were asking about was not normally distributed. the sample of size with the mean, that will be normally distributed. But suppose a simple random sample of size n is drawn from a population with mean mu. So we know if this were the population of the mean of the whole population, and this were the standard deviation of the whole population, when we find the mean of our samples, it turns out when we add up the mean of each sample and find the mean of that, we get the mean of the population. So if 10 of you went out and each asked 50 students, you'd each calculate the average response. Maybe you asked them how many hours did they spend studying. And then we would take the average of those averages, and that would give us a good indication of the population mean. And the standard deviation of what we get is basically the standard deviation of the population divided by the square root of how many we asked. If you each asked 50, then it would be divided by the square root of 50. So you find the standard deviation of all of the means of each of the sets. Say if 10 of you went out, there'd be 10 sets, 10 means. You find the standard deviation of those 10 means. The way that's related to the standard deviation of the population is that'll be equal to the standard deviation of the population divided by the square root of how many you asked, or the number you calculated will be, you multiply that by the square root of n and you get the standard deviation of the population. So if the random variable you're asking about, how many hours you study, we'll use as an example, is normally distributed, then the distribution of the sample means is also normally distributed, no matter what the size of n. If n is large enough, it turns out the mean will be normally distributed anyway, even if your even if the population didn't have a normally distributed variable for that. The central limit theorem says that's the central limit theorem, regardless of the shape of the underlying population, the sampling distribution of the mean of the sample, so you take the mean of all the different samples you took and you graph them, you get a bell-shaped curve. And it becomes approximately normal as the sample size increases. The sample size has to be big enough for this to occur. 5 of you going out and collecting data probably wouldn't make this happen. But 10 or 12 of you going out, we'd be more likely to see that if we distributed these, if we drew a graph of all of the means, like a histogram, we would see that we have an approximately normal distribution of the means of the samples. All right, so important notes about different kinds of distributions, sampling distributions. The sample means target the valuation of the population mean. So if you take a bunch of different samples of the same size, find the average of each sample, and then find the average of those, you are getting close to the population mean. So the means will tend to be normally distributed if you had a sample size of greater than 30. Actually, it's the sample size that affects that central limit theorem. So sample variances also target the population variance with that adjustment, the square root of n adjustment you saw on that formula. So if you are interested in information about a population, you can ask samples and you can get the information about the mean of the population and the variance of the population. They will correlate to each other. That data from the sample will give you information that allows you to draw conclusions about those parameters of the population. The distribution of the sample variances tend to be skewed to the right a little bit, but we're not going to worry about that too much. Our proportion is the fraction of a total that possesses a characteristic. For example, if 12 out of 28 students in a class are female, we say the proportion of students in the class who are female is 12 over 28, or as a decimal 0.4286. If that 28 students was not all of the students in the class, then that would be a p hat. But if that 28 students was the entire population of the class, that would be a p. That's the only difference there. Sample proportions do tend to line up with the population proportion. And we say it's an unbiased estimator. We can use a sample to figure out the proportion in the population. So, sample medians, ranges, standard deviations do not line up with the population. The variance does if we use that adjustment back here for the standard deviation, but the standard deviation itself of the standard deviation of the sample is not the standard deviation of the population. So for the standard deviation of the sample mean, it's the standard deviation of the sample mean is the standard deviation of the population divided by the square root of n. Sometimes that's called the standard error of the mean. That gives you the idea of how far spread out the mean is. And the population has one mean, but you're going to have a bunch of samples and their means are going to be spread out. So the measure of spread kind of tells you how close you are. It's the standard error of the mean. Those are the words. Hopefully this helps you understand that as you read and take a look at this when you go through, have this in front of you when you go through the text. And then we'll talk about doing some problems. I'll do some examples of problems and videos too. But for today, that's all I have. So thank you for joining me in this statistics lesson.